G'day guys, just an update on the power supply. Today I wanted to go over the method of operation, how I'm designing this. We'll start with the transformer. As you can see, it's a split bobbin design. Primary's on the bottom, secondary's on the top. Leaves a piece of plastic between the two. It really helps with the decoupling. Ideally I'd have a copper shield in between the two cores there, the two windings there, and I'd bring that out. And I'd be able to knock off some more common mode noise that gets across that way. But what I've done with this is the best I had on hand. I have grounded the actual transformer itself directly to ground. On the secondary, we have the 0 volt tap getting coupled to ground via a 100 nanofarad disc ceramic. Something I want to go into here just quickly on a little tangent. Sometimes you'll see a disc ceramic, sometimes you'll see a monolithic ceramic, sometimes you'll see a smaller monolithic ceramic. For example, that's a monolithic 100 nanofarad. That's a disc ceramic 100 nanofarad. That's a 105. These are 1 microfarad. Alright? But the point is, the reason you don't see the blue monolithic 100 nanofarad cap here is because it has a lower ESR. And to get the damping factor to make this an effective snubber, I could have used that capacitor with the lower ESR, the little monolithic blue one, 100 nanofarad. And added some resistance in series with it, which would have taken 2 components. Down at 50 Hertz, I just want to actually go into detail on this. I hope I'm not boring you guys, but if we just go over to the LCR meter, how am I going to do this? I am going to set up a camera, guys. I'm not going to do this forever holding the phone. I've literally just started. I'm just trying to give you guys an idea of what's going on in here, and we'll go from there. Let me just find something to put my phone in. Okay, so if we have a look on the LCR meter here, right. Hundred nanofarads down at 100 hertz, which is your rectified 50 hertz. It's also close to 50 hertz. I realise this is on the AC side, so it's saying 50 hertz. But anyways, you get the ballpark. It's close. You know, there's no 50 hertz mode on this meter. But anyway, at 50 hertz, it's got an ESR of 0.390 kiloohms. And if you look at it in parallel mode, which is incorrect, it's way up there. So that capacitor at that frequency has quite a high series resistance to it, which gives it a damping factor, quite a high damping factor, which allows me to decouple this. Couple. The reason I keep saying decouple is because I'm trying to effectively decouple common mode noise from the output of the supply by coupling it away from various areas. Sorry about that. But anyways, I can use 1 component here instead of 2 to get the damping factor I need. Anyways, too much of a tangent there. Sorry guys. So that's the transformer. Obviously on the input of it, there's a MOV across the line. There's a 1 microfarad film cap, and there's a 3.15 fast blow, I think. There's a slow. No, I'm pretty sure it's a fast blow fuse. On the input protection. Transformer outputs go to these 3 relays. Nothing special about this board. LM324 quad op amp. First channel is a buffer for the input, which is time delayed through a RC network going on to the input, so that as you turn your power supply voltage up and down, or if there's fluctuations that are really fast, the op amp's not trying to switch between voltage rails. Then the inputs, obviously there should be input resistors anyway, but they're 10k resistors. And the reason I've done this is because I can then take the input of the op amp on the other side of the 10k resistor straight to a couple of N-channel MOSFETs with 3 diodes and a couple of resistors. And I can hook that up in a configuration where when one op amp turns on, because it's been hooked up as a comparator, when one comparator comes on, it turns the other 2 off when the next one comes on, vice versa. So it can only be outputting one switch at a time. You can only activate 1 relay at a time. And then the relays are also driven by N-channel FETs 2N7000s, if you're wondering. That's just so I can take the smaller voltage here to drive the gate of them. They run off this 12-volt regulator here. Half of its power load's being dissipated on the heatsink it's on, the rest's on that dropper resistor that feeds it. I've done that to minimize the heatsink size. Figured it would be a lot cheaper to use a resistor to get rid of heat than a whole load of aluminium. Can't just use a resistor because I want an accurate 12 volts on my relays. So yeah, you see what's going on there. The 3 trimmer pots, they set the 3 levels for the 3 op amps in the quad pack that they trigger at, the voltages that I want the taps to switch over at. Coming out of there, obviously we're going into the rectifier. It's very hard to see actually. Would help if my phone was charged. I'd have some more light. Oh, what am I saying? I've got a light here. That guy down there with the 2 film caps across it, again, chosen because of their ESR and properties at the given frequency. They're there to minimize diode switching noises. You'll notice there's only 2, not 4, because we don't want to leak AC across the bridge. We just want to shunt it across the input and the output. That goes to this heatsink here with a fan. Goes into this cap bank, 4 4700 microfarad caps plus another one on top. So 5 in total with a 5 kilo ohm dropper resistor. Or a 5.1 kilo ohm resistor. The driver board, that's literally just a prototype. There should be a piece of breadboard in there, honestly. I've got so much stuff to do on that still, it's not even funny. And that board's missing so many traces for what's got to go on it. I probably will be replacing it quite soon. Possibly with a breadboard in the meantime whilst I get things going, because I want to refine it some more. Maybe I'll just etch a design that has a few extra pad locations, as you can see that this one does. But more than that, obviously. I'm not sure yet, but that's the driver board. Basically what you're looking at here is a quad Darlington. You've got 2 output transistors on a heatsink driven by another transistor, driven by another transistor, driven by another transistor. This here is acting as a comparator with this voltage reference. Basically, the voltage reference is running off of a switch mode power supply. I designed this myself. It's got a really, really low output noise. Plus, with the filtering on this, it's down in the noise floor by the output of this. Also, coming out secondary on the other side through this and through this gives me so much common mode rejection. By the time I feed it into the base of this transistor, it comes out so clean that the output is still in the noise floor. So that's what's doing basically the sensing, is that comparator there and the voltage reference. Obviously the sense terminals, the remote sense and the normal sense. The way that's hooked up, by the way, you've got your sensing terminals in the middle of the switch, 10 ohm resistors with 1 microfarad monolithic caps across them going off to the remote sense terminals. And on the other side of the switch, it just goes straight to the 2-wire sense terminals. When the switch is on 2-wire mode, it's shorting out those 10 ohm resistors and caps, so your feedback path's directly going to the output. When you put it on 4-wire mode, these resistors aren't shorted. However, the switch is now connecting the sensing terminals, or the sensing circuitry, directly to the sense terminals. But there is still 10 ohms of resistance between the main output and the sense terminals. So should you come a gutser and pull out, say, your sense terminals whilst you're powering something, or hit the 2-wire, 4-wire switch, power supply is not going to do anything crazy. Yes, it's turned on. Your voltage might drop up 2 to 10 millivolts or something like that. It's not going to make a big difference. You're not going to blow up the thing you're working on. This is the current shunt. I do need to improve this a little bit. Might not have to. It's Constantan wire. I think I use Constantan. Yeah, I use Constantan. And there's a couple of 10 ohm resistors either side of it. A little 0.1 monolithic cap. That's the shunt network on it, just to try and knock out some of the inductance. Get a better feedback loop response. It's a 0.050 ohm shunt. It gets a little bit warm, so I might make a few of them and put them in parallel and use some special techniques. Haven't decided yet, but I'm probably going to go with a Bob Pease style technique on getting a really low inductance on it. But I need it to be that value. For those who don't know who Bob Pease is, I highly recommend you go watch Jim Williams and Bob Pease's videos. They were pioneers of analog electronics and should be highly respected in this field. By the way, the resistor that's hanging off the side here, that's just the output load resistor. That's 820 ohms. Your input load's 5.1k, the output's 820 ohms. This board here, as mentioned in a previous video, this is just a Zener regulator. It's probably going to get replaced with something with more voltage accuracy and the same noise, or maybe more noise if this transistor can not pass it on to its emitter. Oh yeah, it's collector driven. No, that's not going to work. So I might end up basically leaving a design like this, but going a different route where I don't need so many capacitors to smooth out the voltage, and use like a high precision regulator so I get more accuracy. That power supply gives a controlled voltage to the dropper resistor on the collector of the comparator. What else have we got? I think I've gone over this in another video too.